Okay. So welcome and welcome back, everybody. So today is our pleasure to have as our guest speaker Kostas Psaromiligkos, who finished his PhD last summer at the University of Chicago, and now he's a postdoc at Clermont-Ferrand, Université Clermont Auvergne. And he's going to give a series of 2 talks on the formations of the Lafforgue variety. So thank you, Kostas, and we can start.
Thank you, May, and thank you very much to the organizers for inviting me. It is a great honor for me to talk in this seminar. So today we're gonna do an introductory talk. So generally we will talk about Hecke algebras. So this is a kind of algebras that we get from various areas. So they appear in like knot theory, physics, and other areas, but we mostly consider them as coming from reductive groups. So if you're not familiar with reductive groups, just think GLN, SLN, this type of groups. So the methods we will apply are in geometric representation theory, which is, the idea is to study representation theoretic questions using geometry. So what we can do, for example, is parametrize interesting objects by suitable spaces, or understand functions as coming from traces of sheaves, or describe categories of representations as categories of sheaves on certain spaces. And there are a lot of seminal results in the area, like the classification of the reducible characters of finite groups of real type via character sheaves, which, by the way, if you are going to be in the algebra and number theory day in Thessaloniki on the 21st, we're gonna talk there about character sheaves, but there's also the Kasdan-Luz parametrization, the Springer correspondence. So today we will focus on a try for 1. So what we'll do next time is we will construct this Lafforgue variety in the title, which is an affine scheme parametrizing the reducible modules of non-commutative algebras with large centers. So most algebras we get in representation theory have some kind of large center, and in particular, the Hecke algebras we'll consider have large center. And we will show under certain assumptions that the Lafforgue variety varies flatly under a deformation of algebras, and deduce some conjecture for certain cases. So if some of these words do not make any sense today, we will introduce the relevant algebraic geometry that we will need, and we will discuss the theory of Hecke algebras and the type of questions we will see next time. So let me start with the algebraic geometric part. So first, we will need some category theory, because generally we will take some factorial viewpoint in algebraic geometry. This is the usual definition of a category. You just have some objects and morphisms with a composition. Just think of a category of representations of a group, or the category of topological space with continuous maps. Basically, most objects we study belong in some category. And in particular, we want to recall this Yoneda lemma, which is somehow the formal intuition behind this phrase of Grothendieck, that in algebraic geometry, usually you want to look at the morphisms, not at the objects themselves. So what does it formally say? It says if you have a category and you specify some object, you get this functor, the functor that takes any other object and gives you the morphism between them. If you know this functor, then you can uniquely determine the object. So if two supposedly different objects give the same factor, they have to actually be isomorphic. And we will call a factor representable if it somehow comes from this construction. So in particular, we will define affine schemes as just the opposite of the category of commutative rings. But of course, the usual intuition as we have the ring of functions and we consider a corresponding space. We should remember that as well. But today I want to give a different viewpoint that is not always emphasized, which is if we have an affine scheme, we can uniquely determine it from this functor that comes from the Yoneda lemma. As an example, if you take the spectrum of polynomials in two variables, like you probably have heard that this is the affine plane, but from this viewpoint, the idea is that its C points are what? We take C and we input it to this functor. We get homomorphisms from the ring of polynomials in two variables to C. And what are these homomorphisms? Of course, we have to choose just an image for X and an image for Y. So this is why we get a plane. If instead we look at the spectrum of Laurent polynomials in n variables, so we also add an exponent of plus or minus 1, this, we should think of it as invertible elements of C to the n. So this is what we call a torus. Like we take the invertible elements to some power. Now, we also need to introduce what a flat morphism is. So let's say we have a morph between two affine schemes. Then we call it flat if R is flat as an A module. So remember that how we define these things, basically a morphism between affine schemes is just a map from A to R, because we just invert the arrows. So this gives R the structure of an A module. And we call this flat if tensoring with this A module is an exact operation. Generally, we think of flatness in algebraic geometry as continuity in usual topology. It's not smoothness, it's continuity, essentially. Now, if we have more general schemes, not affine schemes, we do the usual thing, we just look at this definition locally. So if we have a scheme X and a scheme S and we have such a map, we can check that just the localizations at points gives us flat maps. So flatness can be checked locally. And another viewpoint I really want to emphasize for this series of talks is that a flat morphism from X to S, we can also think of it as a family. A family of what? Well, given a point in S, we can look at the fiber of this morphism, which we denote by XS. So instead of thinking of this as a whole scheme, we can think of it as a continuously varying family of schemes over S. And many geometric invariants are going to be preserved if we have a flat family. So, as an example, consider this morphism denoted here. I claim this is a flat family of curves. Why? Because I can look at the fiber above a point that's not zero. What I will get the scheme that's like xy is equal to t, and t is non-zero, so what I get are some hyperbolas. And this hyperbola varies with t. The smaller we make t, the closer we will get to the two axes. And in particular, if we take t equals 0, we will just get the union of two axes, because that's xy equals to 0. So this is a family of hyperbolas degenerating to the union of two axes. It is a flat family. It's not a smooth map. It's not a smooth map because the fiber over zero is something singular, as you can see. But it's still a flat. It's still a flat family. It's something continuous. Now, we will need to work a lot with flatness. So what I want to introduce is this notion of Cohen-Macaulay that we need for a very important theorem we'll see later, this miracle flatness. So we call a module Cohen-Macaulay if depth agrees with the dimension. So these are essentially two different notions of dimension in algebraic geometry. Din is the usual dimension, and the depth somehow means if you get your space and start cutting it off with equations, like you can get a three-dimensional space and cut it off with an equation, a priori you're supposed to get a two-dimensional space. You repeat this procedure until you can't continue anymore, and that's your depth. So the depth is generally less than or equal than the dimension, but for very singular spaces, they cannot be equal. We call a module we call a ring Cohen-Macaulay if the two different notions of dimension agree. So vaguely, they do not have two bad singularities, these Cohen-Macaulay schemes. Precisely what we could say if you were in Yorgos Dalesios' talk, you may remember this derived category, there is this dualizing sieve that is the input to, if you're familiar with shared duality, it's the input to shared duality. And maybe you've mostly seen it for curves or projective spaces, but can actually be defined for any scheme. The problem is it has to be defined as in the derived category. And X is Cohen-Macaulay if and only if this is actually a sieve. This is not really important for the talk. It's mostly to be precise, but what's really important is that generally, whichever class of schemes you get that have good singularity theory are going to be Cohen-Macaulay. So polynomial rings, regular rings, complete intersection, or Gorenstein rings, this also appeared in Yorgos' talk, they are all Cohen-Macaulay. Rings with only rational singularities are also Cohen-Macaulay. Now, we need this notion because we have this miracle flatness theorem, which tells us if we have a morphism of schemes such that the base is regular and the fibers are of constant dimension, if X is Cohen-Macaulay, then this morphism is automatically flat. You don't need to do anything else. You just need X to be Cohen-Macaulay and Y to be regular. And actually, this essentially has a converse. If you have such a morphism and F is flat, that's also a way to prove X has to be Cohen-Macaulay. In particular, we will use that next time if you consider some non-commutative algebra that is a finite module over a finitely generated center, then we can get this proposition that H being a Cohen-Macaulay module over the center and Z being a Cohen-Macaulay ring is the same as having some regular subalgebra such that H is a flat A module. So this is, you get this by basically applying nether normalization to Z to get a regular subalgebra, and then miracle flatness will automatically give you that H is flat. Also, something else, miracle flatness is usually stated for local rings. This is a global version. For local rings, it tells us that being flat, for local rings being flat, being free, being projective, these are all the same for reasonable local rings. So being flat is the same thing as being locally free. Now, let me give some examples. So some notions in this talk are going to be somewhat abstract. I will try to just give examples for everything. The scheme that we saw before, it is Cohen-Macaulay. We just took a polynomial ring and we cut off with one equation. We do expect this to be a Cohen-Macaulay ring. And the projection to spec of CT to the affine line we saw before is flat by miracle flatness, if nothing else. It's also easy to show directly, but you can just apply miracle flatness.
Can I ask a question?
Yes, of course. Please ask as many questions as you want.
You're working in for example, in your proposition, but in general, you're working over a fixed ground field. When you say algebras, you mean algebras over C, or is it?
Consider it over any field K that has, let's assume the characteristic is 0 for this talk. In the next talk, we will see some things over characteristic P, but...
And algebraically closed or not? Or not necessarily?
You don't need it to be algebraically closed.
Okay, question.
You don't need it to be algebraically closed. Oh, thank you for the question. Look. No, this doesn't work. Okay. So here's an example of something that's not Cohen-Macaulay. Also give an intuition there. This scheme is what? We need xy to be equal to 0 and xz to be equal to 0. So it's basically either x is equal to 0 or we are in the yz plane. Or y and z have to be 0. So we get the union of an affine plane with a line intersecting. This is not Cohen-Macaulay. Why? This is a really bad singularity. It's not locally equidimensional. If you move to one direction, you have a two-dimensional thing. If you move to the other direction, you have a one-dimensional thing. So in particular, you could not get some flat morphism to C or C to the line or the plane. And here's an example we will actually see next time, just to see how general this criterion is. So this wheel scheme is also Cohen-Macaulay. It's Cohen-Macaulay because this is something regular and you cut off here by a well enough equation to get something Cohen-Macaulay. So if you take the projection of that to the affine line minus a point, it will turn out to be flat by miracle flatness. We will see more on this next time. Any questions on this part of the talk? So let me move to this quad scheme that we will use next time to construct our spaces. So generally, schemes, any kind of algebraic space can also be defined as some kind of representable functor. And usually, you've probably heard the phrase moduli problem. What we mean by that is take a reasonable functor and show its representability. So it actually comes from some reasonable algebraic space. This definition is what a flat family of quotients is. And it means the following thing. So we have, as you see, an X over S schemes. Then we get some map from some T to S. You should think of this as the base space, the parametrizing space as before that we were considering families over. So if you do that, you have a fiber product, because the category of schemes admits that, like this. Now, E is a coherent CF on X, so E lives here, and we want the family of quotients of E. What we will do is we pull back E to this fiber product, And then we want some surjective homomorphism here. Why? Because if you localize this at any, if you consider the fiber of this over any point of t, you will in particular get an actual quotient. And as you vary t, you get a family of them. If coherent sieves and schemes, you're not used to this language, well, if assume X and S are some kind of affine scheme, let's say the spectrum of A, then what does it mean a coherent sieve on X? That just means an A module. So you can consider these schemes to be affine and consider it just as an A, just an A module. So this is what is a flat family of quotients, and we also have to specify when we consider two of them equivalent, but this is what you would expect. Like in these quotients, you have ET, and you have two different maps. So we consider they are isomorphic if there is an isomorphism here, making this thing commute. So we define a functor, a moduli functor, by taking such a triple, a scheme X over S and a coherent sieve on X. We consider the quad functor taking a scheme T over S and setting it to all these flat families. A great theorem of Grothendieck is that this functor is actually representable by a proper scheme over S, a proper int scheme, but that just, in this case, it means it's a union of infinitely many proper schemes. In particular, recall that before we said that a lot of things stay invariant in a flat family. So, for example, the Hilbert polynomial is one of them. If you want to actually get a proper scheme, you should specify a Hilbert polynomial because it cannot vary in a connected component and get different proper connected components for each one of them. We'll use this quad scheme next time. Let me just mention there are more familiar schemes that are particular instances of quad schemes, such as the Grassmannian. The Grassmannian, which parameterizes k-dimensional subspace of a space, is basically a quad scheme if you consider just the spaces to be somehow trivial and you consider the structure shift to the case. So you identify a plane with the quotient that it defines from the space. And you get the Grassmannian as a quad scheme. Of course, that's not really a proof of the representability of the Grassmannian. You use the representability of the Grassmannian to prove the quad scheme is representable. But the Grassmannian is an instance of a quad scheme. And another object that is also more familiar is we have the Hilbert functor that parametrizes flat families of proper subscheme of X, like the Hilbert scheme of points. And even in this generality, we have that it is also representable by a proper scheme, just by looking at the quad scheme and inputting in place of phi, you put the structure shift. Just because a closed subscheme, like in the affine case, a closed subscheme will be defined by some ideal, and you can look at this as a quotient. So next time, we will actually define a non-commutative version of the Hilbert scheme that applies to modules of non-commutative algebras. And we will use the quad scheme to prove the representability of this non-commutative Hilbert scheme. It will be a basic input in our proof of our main theorem about the existence of this affine scheme. I think this is the last slide of algebraic geometry. So any questions on the first part?
Okay, can I make a question? How easily is it to make all these actually all these are more or less kind of moduli spaces, right? Characterized. Yes. How easily it is from this abstract definition to get actual equations, let's say, or like the first example here, or it's
usually
it's hard.
Usually it's basically impossible if you take a very complicated space. If you get something like even the Hilbert scheme of points,
right.
For a large space, it's something really singular.
Okay.
But they are very useful. Like what we'll do next time is this quad scheme is so general that a lot of things that we like are just closed in this quad scheme.
Okay.
So you get the representability of a bunch of moduli functors for free.
Okay, good. Okay, thanks.
Thank you for the question. So the next part, actually, a lot of people will find it more elementary than the first part. And we're going to talk about Hecke algebras. So first, some more category theory. If we have an abelian category that has arbitrary direct sums, we call an object a finitely generated projective generator if it satisfies this condition. And what is important is this theorem that if you have an abelian category that has such a generator, then you can write it as a category of modules over an algebra. And this theorem allows us to get a bunch of categories of representations of Hecke algebras, like from finite reductive groups, from smooth p-adic representations in particular, and it's okay if you're not interested in any of this. If you have a finite group of Lie type, unipotent representations comes as modules over a finite Hecke algebra. If Ivahori representations for p-adic groups are modules over an affine Hecke algebra. And generally, if you have a reductive p-adic group, so let's say GLN over QP, we only care about its smooth representation, its some continuity assumptions, and the whole category breaks into blocks that are given by modules over affine Hecke algebras. But, okay, I guess this raises the question, what actually are these Hecke algebras? And to define them, we need to start with Coxeter groups. Coxeter groups is something really basic. You have a set of reflections that generate a group under these relations. So what do I mean by reflections? In particular, MII has to always be 2 because we want, actually, no, MII will always be 1 because you want SI squared to be 1. So this should also be 1. Like Sn is a Coxeter group. It's generated by the elementary reflections 1, 2, 2, 3, and so on and so on. And they satisfy, well, they're obviously reflections, but they also satisfy this. And finite and affine Weil groups of reductive groups are also Coxeter groups. We'll see what that is. But for SL2, I just give this example. They are S2 and this semi-direct product. Where do we get Coxeter groups? Well, from various sources, but often we get it from root data, which is some kind of combinatorial structure coming usually from reductive groups. Some people study them independently, but usually you get them from reductive groups. Now, if we have a Coxeter group, we can already define a Hecke algebra, and it's just an algebra satisfying these relations, nothing else. And this, we always say it's a deformation of the group algebra. Why is it a deformation of the group algebra? Because if you put Q equals to 1 here, what you'll get is T squared is equal to 1. So if you have T squared is equal to 1 and this relation, these were basically your relations in the group. But we often want to specialize Q to something else. So it looks like varying Q should give you fairly different algebras. In reality, though, if you assume your group is finite, this is important. We know where here assume these Coxeter groups have to be finite. So in particular, this Z R times S2 is not a finite group. We saw before. If it's a finite Coxeter group and Q is not a root of unity, then actually all these algebras are just a group algebra. And while this looks surprising, it has to do with the fact that these are finite dimensional algebras. So if you have the same representation theory in terms of dimensions by the Artin-Wedderbe theorem, if these things are semi-simple, and that's why you assume Q is not a root of unity, to get a semi-simple thing, then they have to be actually the same. So this is the classical version of Tits deformation theorem. We will see later a more general version of this, and also an even more general version that we're proving right now.
So Kostas, sorry, this Q is something fixed in some over C, right? It's a fixed number. It's not a parameter. Or...
You can think of it as a parameter. We'll take both viewpoints. You can think of it as a parameter, and this algebra just an algebra with Q being a variable.
Okay.
Or you can specialize it to get a specific algebra.
Okay, thanks. Okay.
So if you specialize it to something that's not a root of unity, we get a group algebra.
Okay, thank you.
You're welcome. So I mentioned before we get them from root data. What are root data? Let me start by saying what is a root system, and I'll show this just with a picture because the definition is not particularly nice sometimes. So here I have this group, this exceptional group G2, just to get an interesting root system. But if you have GL2, you should get basically that, and like SL2 should be something like this. So if you have a reductive group, let's say GLN, inside of it, you have a torus. So the diagonal matrices for GLN. Basically something, at least over an algebraic closed field, that is like F star to the n, where F is your field. You specify this torus, and then this root system very vaguely tells you how to build the whole group out of a bunch of SL2s that you understand. In particular, you just look at the characters of this torus, which give you some lattice, which gives you basically Z to the n. And in this lattice, you keep particular characters that you call roots. You make a choice of simple roots, in this case A1 and A2, and what you should get is that everything else comes from adding these things with some integer linear combination. When you specify simple roots, you also get a set of positive roots, which is everything that is on this side of this line, the ones that have positive coefficients. And each of these simple roots will also give you a reflection. It has a corresponding reflection, which we call SA1, and it should preserve the root system. So if you take a reflection across this line, this SA1, you see that every root goes to a root. Now, the reason I try to first introduce this with a picture is that we have this actual maybe it looks horrible definition of a root datum. So what is that? Well, this is supposed to be a root system, and this is supposed to be a dual root system. So we just focus on the first part for a while. But you should think of them as being dual. In particular, X star should be some Z lattice. And X lower star should be the dual lattice. And this duality should be given by this perfect pairing. But then you also require some other things. Phi and phi star, these roots and coroots, as we call them, they are just finite subsets, which we require the duality to send roots to coroots. So we also specify a bijection here that has a particular pairing. And the final condition is about this reflection we said before. It has to preserve the root datum. These reflections that we get from simple roots, they should preserve the root datum. Now, if you have this complicated quadruple of things, you have two naturally defined Coxeter groups. The finite Weil group, which is just a group generated by the SA, and an affine Weil group, which is the same thing, you just get a semi-direct product with this X star. So in particular, recall that the root datum for SL2 was, we said it had one root, one single positive root and its opposite. Since you only have one root, you have one reflection, your Weil group has to obviously be S2. And then a torus for SL2, diagonal matrices, is something one-dimensional because you're in SL2. So your lattice X star is also one-dimensional, which is why you get a Z. So that's the affine Weil group you get from SL2. If you look at GL2, then you would get a two-dimensional lattice, but the Weil group would still be S2. So this is what root data are, and the next slide is going to be the last technical slide of this talk, which is what actually affine Hecke algebras are. So you still need a little more data. You need this pair of functions in roots that you want them to be W invariant, and these technical conditions here, often lambda and lambda star are just equal. So you can, for the moment, just ignore any other case and just assume they're equal. So then we can define an affine Hecke algebra. How? We get Cx star and this Hecke algebra we defined before of the finite value. Now, the multiplication is given as follows. Cx star and HWQ are subalgebras, so they just have their natural multiplication. And if we multiply, we need to specify how these two interact. They interact with this equation. Now, I know this looks horrible, but let me make a couple of observations. First of all, this whole part is abelian. And we only have finitely many things above it because this is a finite dimensional algebra. And also, this relation, it may look horrible, but assume X for now, say it's W invariant. Acting on X with anything just preserves. Then, theta of SAX is the same as theta X. So this term here vanishes. In particular, this whole right-hand side is equal to 0. And the left-hand side is just a commutator. So if X is W invariant, this tells us theta X is actually in the center. It commutes with everything because it commutes everything in here, commutes with everything in here, because this algebra is abelian. and it commutes with all these operators generating the other part. So for one, this relation gives us the W invariant elements are in the center. And also notice that if these two are equal, this large part simplifies by a lot. This becomes 1. This just becomes Q to the lambda A. You can group these two things together. It simplifies by a lot. So let me just gather up these observations. The large part can simplify. They have a large abelian subalgebra. And for reasons that will be obvious later, they have a large center, which I want to write it in another way. So we saw that W invariant elements are in the center. We didn't see the center is equal to that. This is actually the content of the classical Satake isomorphism. And we can write that as regular functions on this scheme. This is called the GAT quotient. And GAT quotient basically means take W invariant in the ring of functions. If you think about this, this makes sense because in algebraic geometry, we look at the rings of functions. So when you quotient by a group, what are your new functions? You would expect they are the functions that are invariant under the action of the group. So you define the quotient that way, and it satisfies a lot of reasonable properties, but just by definition, T mod W will be the spectrum of this. So in particular, the center is regular functions on T mod W. And lastly, for an affine Hecke algebra, we don't have the classical Teach deformation theorem anymore. In particular, if you specialize Q to different parameters, the algebras you get are not even Morita equivalent. You do anyway have some more general form of the Teach deformation theorem. I was introduced to that by Mary and Irini last year. There's a great book by Hecke and Pfeiffer that has a more general version, and it can still work for an affine Hecke algebra. It will give you that irreducible representation should be the same as a set. Let's say that if you specialize to Q not being a root of unity, if you specialize to Q outside some particular subset, then you have some version of the Teach deformation theorem. What we will see next time is something more general than that. Anyway, so, okay, these algebras look very complicated, even though they can be simplified sometimes. How do we work the representation theory? Well, a main idea is let's take advantage of this large center and abelian part. And let me introduce this method by a very concrete example. Let F be a non-Archimedean local field. You can just consider it to be QP. Then the Vahori-Hecke algebra of SL to F is just going to be this very specific algebra. So you have the ring of Laurent polynomials, and you have one and TS, which satisfy these two relations. In particular, there's no point in thinking about TS squared. TS squared simplifies by this relation. The center of this will be symmetric Laurent polynomials, because it's R mod W, W invariance of R. And as we saw before, we can think of that as regular functions on this torus, on C star quotient by S2. Now, how do we work out the representation theory? Well, assume V is a simple module. Just take V to be a generalized eigenvector of R. I can do this because R is abelian. Well, in this case, R is, you just have to look at X, but generally you can do this for an abelian algebra. And consider XV is AV. I claim these two vectors, V and TSV, linearly generate the whole space. Why? Because the module is simple. That means any vector can be written as HV for some H in the algebra. But every H in the algebra can be written as some element of R plus TS, some other element of R. Why? Because, well, TS squared is not a thing, it simplifies. And I can use this relation over here to carry elements of R on the one side of TS to the other side of TS. That's how you should think of these intertwining relations. We can pass elements from the one side to the other. So any element of H is of this form, in particular HV is generated by V and TSV. So we have this simple module. There are three cases. Either the dimension is actually 2, and then we have to check our module is reducible, and it actually will be except if A is -1 or the square root of Q. I'm saying one module for it. I mean, one module for this and one module for this, because A is not, you should not think of it as an element of C star. You should think of it as an element of C star mod S2. Why? Because we just want an eigenvalue of X, but if A is an eigenvalue of X, A minus 1 is also an eigenvalue of X. So I really care about this pair, not about the one value in particular, which is why A should be thought about as living in this quotient. So, okay, I have a bunch of two-dimensional simple modules. When do I get one-dimensional module? Well, if my module is one-dimensional, TS should also act as a scalar. And by this equation, this scalar either has to be -1 or Q. It cannot be anything else. And I get two modules in each of these cases. So a hint for the other time, if I draw this, it's going to look something like this. So these are the four representations that do not live in this line. I should remove some points here. And this should be all the representations. Now, this method generalizes abstractly in the following way. Consider a simple module. The center, by Schur lemma, acts via character. And Bernstein's idea is basically the following. Okay, as you saw, even for SL2, we get a lot of modules. It's not some finite thing. But if you specify a central character, then you don't get that many modules. Like if you specify A, you have finitely many modules. In general, if you fix the central character, the character via which the center acts, this is a formal analog of our previous procedure. You consider just a one-dimensional module corresponding to the character, and you induce it to the whole of H. This is a functor that is adjoint to restriction, and in particular, to restricting from H to R, and in particular, you have this proposition by Bernstein that tells you any simple module can be embedded in some of these induced modules. So what are these induced modules? You get one for each central character. It's the analog of in our previous example, the two-dimensional modules. And you can also think of it, if you remember this lemma that we said, that if you have a finitely generated progenerator, you can consider this as a kind of universal module over the algebra. And M here is that universal module specialized at the character here. So by this proposition, since every simple module embeds in M here, we can just study this M here. In our example, and actually in general, this module was irreducible generically. It was irreducible almost everywhere. So a natural question is, when exactly is the induced module irreducible? And there are various cases a lot of people have worked on this. I've included some names: Bernstein, Deligne, Kasdan, Lustig, Kato. In the example we saw, you need x to not be -1 or square root of q. Now, consider the following thing. Let's go back to affine Hecke algebras. Fix some root datum and some parameters, and let HQ denote this affine Hecke algebra. Then the center is going to be regular functions of T mod W, and you have to adjoin this Q. Of course, Q is in the center, it's a variable. Then, if you specialize the algebra at T, you can look at T mod W. Remember, we look at schemes in this talk mainly using this functor of points thing, this functor of points formally. So this is spec of Rw. And what is a point of T mod W? A point of T mod W is a character from Rw. Let's say a K point. It's a character from the center to K. So we can look at this torus as parametrizing the possible central characters. Now, if we fix we fix a Q to be T, we can look at the subset of characters that give a reducible module. And what we'll get, this is also very classical, we'll prove it next time though. What we'll get is a closed subscheme of T mod W. So for each specialization at T, we get some closed subscheme. And Aubert, Baum and Plymen made the following conjecture, that for an affine Hecke algebra, there is a flat family of schemes that essentially starts from x1 and also contains x square root of q. Why this particular one? Well, x1, as we saw, is some group algebra of a semi-direct product. We understand group algebras. And this will give us the Lafforgue-Hecke algebras that we are interested in. So we would like to have a flat family deforming this reducibility log between something we understand and something that we want to know. This is a weak version of the conjecture. They actually also require some things from this family. But we will see that next time. So let me make some more. So we expect this YT. Why didn't I denote? Why didn't I use this XT? Actually, we don't want to get exactly xt. Sometimes for these bad specializations at roots of unity, we will get things that are not reduced. We will get singularities. So for easiness, I will just ask for a flat family, but of course it will closely be related to a family of deformation loci. So this conjecture was proven by Aubert, Baum and Plymen in 2007 for the Lafforgue-Hecke algebras of GLN of SL2 and for the exceptional group G2. What we will do next time is prove it in the case where the center is regular. This includes the previously known cases, and it also includes Hecke algebras that come from reductive groups that are adjoint, whatever that means. They're dually simply connected. These are some references, and that is all. Thank you all for listening.
Let me stop the recording.